Okay, so last time we started this improper integration. For comparison, what have done before, we consider a function fx continuous on an interval. Okay, so this is closed and finite. You say bounded. In this case, we have the theorem f is integrable. And to find the integral, if f is the function, a smooth function, we can find the antiderivative of the fundamental theorem of calculus. Now we want to extend this. So the first extension, they will allow the interval to be unbounded. We could integrate a to infinity fx. Whether it's integrable or not, it depends on the limit. We still start with a finite interval. We end at b. Then we let this upper limit go to infinity. If this limit exists, and in this case, we see this integral is convergent. Okay. An example we had last time is Zichen. Can you hear us, Zichen?
Yeah.
Okay, turn on the camera. So to find this integral to determine it's convergent or not, we start with the finite interval integral from 1 to b. Okay. For this one, use the fundamental theorem of calculus. And we can find the limit when we go to infinity, it is 1. Therefore, we see this convergence into is convergent. And we have the integral. In the same way, we found this integral. We start with this interval find the antiderivative. Have the same conclusion. The third example we had is when for this one we find the integral on a finite interval logarithm x. However, this time it diverges. We conclude the integral is not convergent, it's divergent. Okay, so two different cases. One convergent, convergent. Second, divergent. You can see it's different from what we had before. If it's a continuous function on a closed and bounded interval, it's always integrable, always converges. However, if it's an infinite interval, sometimes it's convergent, but sometimes it may be divergent. Should be careful what you have. Okay, question, Sophia and Zichen?
No.
No? Okay. So this is the one side case. We can also define the integral net infinity to b in the same approach as the limit. Again, if the limit exists. Looks very natural. A tricky one is the two sides. This can be defined as one side stop at 0 and restart at 0. So this new improper integral is defined as the addition of the two if both exist. Okay. It might be very tempting to define the following, not equivalent. So the tricky thing, even if this limit exists, this integral may still be divergent. A typical example is for this one, because we can integrate it 1/2 x squared. X squared, the value at b and a negative b are the same. So the difference will be 0. For this function, the integral is 0 for any b. In particular, the limit exists. However, the integral is not integrable. So the limit zero, but divergent. Because if you check the one side integral, both are divergent. Okay. And a very useful formula. This represents the area of the domain under this graph. It's an infinite extended domain. However, the area is finite. Okay, so we can check. Okay, so that's the first type of generalization. We allow the domain to be an infinite, to be unbounded. The second type of generalization, we allow the function to be discontinuous at the endpoint. It's possible that the function is not defined at the endpoint. It may go to infinity. It may oscillate. In this case, again, we can define the integral. It has the same terminology, but it's in different meaning when f is not continuous at the endpoint. This should be as the limit of the one side. Let's see an example. Okay. Okay, so this function 1 over the square root 1 minus x. If x is 0, we're at 1. But if x increase, denominator decrease, is 1 over this increase. On each t this function is continuous on the interval from 0 to t. So in particular, we can integrate. So now let's pick find the integral from 0 to t. Okay, let's guess how to find this integral. Sophia, what a method would you pick? It's not okay. It's a little bit strange. It's square root of 1 minus x. We would guess. Okay, let's guess one. Let's guess one antiderivative.
Sine negative arc sine.
Okay, okay, that will be my next exercise. Next exercise, if I have a square, that's arc sine. So this time is if it's just a square root, what do you have?
X to the -3.
Okay,
No,
okay,
X to the -1.
okay, let's give me 1 second. Let me write it down. This is f. If we have this, what's the antiderivative? Then we make corrections. Okay, for the first one, what's the antiderivative? So first, what's the power? We want to be negative 1/2. Yes, okay, that's the first step. We get the correct power. Okay, now we need to fix the coefficient.
2.
Okay, nice. Okay, now let's compare with the next one. It should be similar. So it will be 1 minus x. What's the power?
1/2.
Again, this will be 1/2. Now let's figure what the coefficient should be.
2.
If we have 2, okay, that's the first, that's partially correct. Okay, that's good progress. Okay, now let's take a derivative, see what we get. If we take a derivative of this, 1/2 canceled, -1, the power is correct, and the chain rule will give us another -1, right?
Oh.
So we have an additional -1 to correct. How do you correct this?
Just -2.
Yes, okay, very good. You see, that's how we find this antiderivative. We start from something we know, then we get something similar, and make corrections, and the corrections, we will get the formula. So try and correct, try and correct. Okay, so we have the antiderivative. We can apply the fundamental theorem. This will be -2 -2 1 minus 0. With the negative sign actually will be 2 minus. Tuchen, are you following? Are you questions, Tuchen? Okay, okay. Maybe she said something that she can add. Okay, now let's see what's the limit if t goes to 1. Okay,
Two.
Sophia, what?
Two.
Okay, yes. So if t goes to 1, 1 minus 1 is 0. So this converges to 2 as okay, now we go back to the initial integral. This function is not continuous at 1. When x approaches 1, the value goes to infinity. So it's not continuous at this point. However, we found the integral from 0 to t. After we found this integral, we take a limit, we get a finite value. This implies the integral is convergent. And we have found the value. Okay, so that's the first one. The second one, okay, as we have just mentioned, the integral 0 to 1. First, Zichen, if this function continues on the interval, unmute yourself, Zichen.
Wait, what's the question? I don't know.
If this continues on this interval, is it continuous at 1?
No.
No, it's not even defined at 1. So when x approaches 1, this approaches 0, this approaches infinity, it's not continuous. So this function is not continuous. Not even defined. Okay. So this is an improper integral. So to do this, we will do the integral from 0 to t. Okay, Sophia, you tried this before. What's the antiderivative for this function?
Arc sine.
Arc sine. So we found the arc sine from 0 to t. Arc sine t. Arc sine 0. Arc sine 0 to 0. So it's arc sine t. Now what happens when t go to 1? This continues at 1. It's arc sine 1. Okay. Who knows the value of this arc sine at 1?
Wait, is it pi over 2?
Because sine pi over 2 is 1. Okay, so this is pi over 2. Okay, now see what we have achieved. This integral is arc sine t, which converges to pi over 2 when t increases to 1. Therefore, this is convergent and it converges to pi over 2. So the conclusion even though the function is not continuous at 1, but we treated it as the limit of this definite integral. Okay, a similar case, if f is not continuous. At a, this improper integral is defined as a limit decrease to a from positive side. We first find this integral, then we let the lower limit approach a. If this limit exists, then we say this improper integral is convergent. Another case, at some interior point, in this case, we can define the improper integral on the whole interval as addition of this part with this part, if both exist, as we have done before. Okay, let's try another example. This is second, third. Okay, Sophia, is this a proper integral or improper integral?
Proper.
Why is that?
Oh. Oh, improper.
Improper. We can say when x is 1, the denominator will be 0. It's not defined. Okay, so it's improper. So now to check whether it's convergent or not, we start with the finite one, 0 to t. Okay, now we want to apply the fundamental theorem of calculus. We need to come up with an antiderivative of this, something the derivative is this. What's that function? How to guess this one? Again, we start with something simpler. If this whole thing is u, 1 over u, what's the antiderivative?
Natural log.
1 over u, natural log. Now it's 1 over 1 minus x. What's the antiderivative? And on our interval, u will be positive. So let's simplify this a little bit. It will be logarithm u if u is positive. We guess 1 minus x. Now we make corrections. What's the coefficient? We want to put some.
Negative.
Nice. Okay, so that's the antiderivative. Here the t. So it is negative. Logarithm 1, which will be 0. This will be. Now let's see what happens if t go to 1. Now minus. T becomes larger and larger, it approaches 1. Zichen, what happens to 1 minus t? T goes bigger and bigger. This will become smaller and smaller, and gradually become 0. Sophia, if this goes to 0, what happens to logarithm?
It's it's divergent.
Okay, so with this divergent. Therefore, this integral, 0 to 1, this improper integral is divergent. Okay, one more example about this improper integral. Okay, first let's check, is this a proper or improper?
Improper.
Why?
Because when x is 0, it's not defined.
Okay, at x 0, nice. So we have to use the limit. Let's find the limit. T to 1. Okay, what's the antiderivative of logarithm x? Okay, f, let's try to recall x logarithm x dx. Okay, what's this? Any idea? Okay, now let's recall, how do we find this indefinite integral? What method would we use? Logarithm. We want to apply the fundamental theorem, but it's not applicable. We don't know anything about this. We know the derivative, but we don't know the antiderivative. We have learned several techniques. First one, integration by parts. Could we do that?
Oh, you do ln x and 1.
Okay, integration by part. This will be our f is g derivative. So g is x, f g, f derivative g dx. This will be x logarithm x 1 over x dx. Okay, so one antiderivative of this is x logarithm x minus x t 1. Okay, when you evaluate at 1 is log 1 logarithm 1 minus 1 minus t logarithm t minus t. Simplify 0 negative 1 minus t. Now we need to find the limit when t go to 0. Negative 1 is negative 1. What's the limit of this when t go to 0?
Zero.
Okay, nice. Minus 0 plus 0, negative 1. Okay, if you forget, you should be able to check this is 0. Confirm this. Okay, now we found that this limit, we conclude. Okay, Sophia, what's the conclusion about this one? Convergent or divergent? We found the limit.
Convergent.
Yes, the limit exists, so this is convergent. This is a very strange function. If we graph this logarithm, so what the integral tells us is that the total area, it will be negative 1. So the absolute area of this will be 1 because it's under the line, so it's negative. Okay. So it means total area. Okay. Very useful information. Zhen, you have been very quiet. Any thoughts? Any questions?
Not really.
Okay. So this one very interesting, not simple. The definite integral of this improper interval. Okay. So next, we will start a new chapter about the differential equations. Okay. So let's consider a problem. Consider that we have some container in some lab, and there is some virus growing in this lab. Okay, some virus. We want to see how the population of the virus changes in time. So PT population. Okay, so when T changes, the population changes, we get a function. Okay. To find a formula for this, we make some simplifying assumption. For example, we assume there's a limited environment, even though it's limited, but when the number is small, we can view this as a limited environment for the virus. And we will make a corrections to our assumption later. For simplification, will be corrected later. It may be modified. Okay. So we want to get our calculations moving. Okay, so with this, we have our model. What's the model of this population? The model is the change rate to be the derivative is proportional. I mean, more virus, the number grows more quickly. So that is proportional to this number. We will use the following notation. P derivative. So whenever you see two quantities with this relation, it means they are proportional. So we call this process assumption and model. We establish a model for this question. Okay, let me check. Sophia, have you heard this term before, model?
Maybe.
Okay, there's a very famous saying about this, is all models are wrong. But some are useful. So you can see, especially it applies to our case. we make a very strong assumption. Assume there's unlimited environment. In particular, it's not realistic. Our Earth, maybe our lab, or maybe the country, we have a limited environment. So in this sense, our model is wrong. But it does give us some insight to how population changes. In this sense, we say our model is useful. Okay. So we have the model. Now we want to write it as a mathematical formula. Formula, the derivative is proportional to p. We use this p derivative. So here k is a constant. Determined by the virus. If k is positive, as in our virus case, we have the growth. K is negative, we have the decrease. Two different models. Okay, so we can see how we changed it. Initially, we have some question about the population of certain virus in a container. That's where we start. And we make some assumptions to simplify this model. Because some things we can start with the model. Then we have a formula that's derived from the model. This formula, first it's an equation. It's an equation about the unknown population function. This equation also involves the derivative. Because of this, we call it a differential equation. So this is our first differential equation. It's an equation involves a differential equation. It's an equation involves the derivative of the unknown population function. Okay, we will have 5 minutes break. After the break, we'll see how to solve this differential equation. Okay, 55. Okay. So now how do we solve our equation? We have a derivative here. One attempt would be we integrate both sides. And this is the function p. Give you an integration constant. However, now we have an equation about this unknown function. We don't know how to solve it from the equation. Not solve. Okay. We want to utilize what we have learned in the previous chapters. To do that, we need to separate the two variables, p and t. So the method okay, so we rewrite this using the definition of the derivative d dt. Okay. Okay. Now we have two variables, the independent variable t and the dependent variable p. We want to separate the two variables. We will put t on one side and p on the other side. This is separate dp over p. Okay, let's see how we moved from the differential equation to here. I separate this dt to the right-hand side and divide both sides by p. Sophia, any question about this step? No? Okay, so this is the separation of the variables. On the left, we only have the dependent variable. There's no t over there. On the right, we only have the independent variable. There's no p over there. So this step equals the separation of the variables. Now it's separated. We can integrate. So the integral dp over p will be the integral k dt. Okay, Sophia, what's the integral of this one? K is a constant dt. What's this?
It's 0.
That's the derivative. What's the integral?
It's kx.
In this case, we use the variable t.
kt.
Kt plus c. And Zichen, what's the integral of this one? Ask you to unmute. If not, I'm going to ask Sophia. Sophia, what's this one?
Oh.
Okay, Zichen, okay, Zichen is ready. Okay. You don't know. Okay, so something whose derivative is 1 over p. Okay, if it's 1 over x dx, what's this? 子晨，
log of x.
log x plus c. Now we just change everything to p. Okay, what's the integral? If we change everything to p. In our case, it's a little bit special because p represents the population. So p cannot be negative. We can use logarithm p plus c since. Okay, so from the differential equation, the separation of the two variables, then we take integral of the left side, integral of the right-hand side, we get a new equation. So again, we have two integral constant. We just need to keep one of them. I keep the first one. This, we solve the different equation. We take a logarithm, we get the p the exponential. Then using the properties of exponential function, e to the c, e to the kt. Again, this is an integral constant. We can relabel this. Keep in mind the c will be positive. With this relabel, pt. Okay, that's how we solve this differential equation. The solution is this. We have a positive integral constant. So how to find this constant? We use something called the initial condition. At time 0, the initial condition, you will have the initial population. Then we can use this to find the constant. Therefore, the solution of this. Okay, summary. We have the differential equation. We have the initial condition. Okay, so this DE stands for differential equation. This is a differential equation. And IC stands for initial condition. Put them together, we call this an initial value problem. So it means we are given the initial condition and we give the differential equation. We want to find the general population at any time. And we have a solved solution. So this constant is the initial condition. Okay, that's our solution of the initial value problem. In the future, maybe we'll use IVP for short. Initial value problem. And we can check. This satisfies the initial condition. Sophia, how do you verify this? That this function satisfies this condition.
You plug in 0?
You plug in 0, 0, what do you get?
You get PO, a P0.
P0, okay, so it satisfies the condition. Zichen, how do you check if this satisfies the differential equation?
I'm not sure.
So we plug this into the right-hand side, and we take a derivative of the left-hand side. We compare if they are the same. Check. The derivative. The derivative of coefficient, chain rule, and the right-hand side, Kp. Kp naught. And we check they are the same. Similarly, P naught. Initial condition, check. Okay, so this is how we solve our first problem in differential equation. The method is separation of variables. Okay, any question about this example? Sophia, questions?
No.
Okay, so the modeling, have the model, then we have to know how to solve the different equation. Okay, as we mentioned, we make some very strong assumptions. Now we will modify our model. We make it more realistic. Okay, improve the model. Same setup. Some virus. So previously we assumed the derivative is proportional to P when this P is small. Now we make an additional assumption. We assume there's a capacity of this container. So how large the population can be? We call this M, a very large number. Now, if our population has grown close to the capacity, Then there's a severe competition that limited the food source. In any way, this will grow slower and slower. The worst case, if we put maybe too large amount of virus in a small container, the number will decay. Okay, so is proportional to m minus p. Does this make sense? The two scenarios. In the early stage, the population grows. The more we have, the faster it grows. But in the later stage, it grows so much, it almost reaches the capacity. Then the rate will be slower and slower. Sophia, what do you say about this model? Does it make sense?
Yeah.
Okay, so it's an improved version of what we had before. Now we want to combine the two effects. So the combination proportional to the product. Again, let's recall what we have mentioned before. All models are wrong, some are useful. So this is more useful than the previous one. Okay. Then we have the formula, mathematical formula. Okay. A new differential equation. Okay. Again, we can supply the initial condition. Then put them together. We have our second initial value problem. Okay. Next, we will try to solve this differential equation. Any method came to your mind? How to solve this one? Sophia, what method do we have? We learned a very new method because the separation of the variables. Let's try to separate the two variables. We want to put all p on one side, t on the other side. Separation of the variables. Okay, then the integral should be the same. The integral p k dt. The first one, the right-hand side is exactly the same we have before. We know this quite well. How do we integrate this one? in this formula, m is the capacity, m is a constant. What method do we have to find this indefinite interval? Okay, yeah, Sophia, what, any guess? How do we move forward from here? The techniques we learned in chapter 7, what are they? Which one is applicable?
By parts.
Okay, partial fraction.
Oh,
So, okay, so here is the rational function of a decomposition. So here we can apply the partial fraction decomposition. So how do we decompose this? Pm minus p will be something p something.
oh, it was p and m minus p, yeah.
Okay. So how do we find a and b?
We create a
get-
equation.
Okay, get rid of the denominator. It will be a minus p b p. This is am minus a plus b p. Okay, so now this side is a function of p. On this side, what's the coefficient of p, Sophia? There's no p over there. The coefficient should be 0.
Oh,
So no p, we see that 0 is, and the constant term is 1 am. So now we can see a is 1 over m. And then this implies b equals a. So we have the partial fraction decomposition. 1 over m the integral of this rational function. Okay, will be the combination of the integrals 1 over m. So this is minus okay. Okay. So now we put them together. We have an implicit solution of our differential equation. This it equals kt. So I'm going to copy all of them. Okay, p is positive, so we can drop this absolute value. For the second one, let's make an assumption for the moment that p is also less m. So we can drop the absolute value. So this is an assumption. To simplify our expression, I'm going to multiply both sides by m. And I will relabel the coefficients. I will relabel this. And relabel C. And I will use the property of the logarithm. This will be so what I'm doing now is we have found an implicit solution, an implicit solution. Now we want to find an explicit solution to solve P from the equation. Take exponential. In the process, I will make some simplifying assumptions. Again, I make the relabel. So P. Well, not done was okay. Now, how do we solve P from this equation? Sophia, what would you do?
We multiply both sides with m minus, no.
Yeah, that works. That works. M minus P would distribute to get.
You distribute and then you subtract, and then you add P, P times C e to kt on both sides, and then factor out P.
So P will be CM. Okay, to simplify this a little bit, I'm going to divide both numerator and denominator with this factor. These two all goes away. We have only one term over there. So this is our solution of the differential equation. And okay, we'll have more about this next time. We'll see how this proposition changes when t changes. Okay, let's check. Okay, when t increases, Sophia, what does this term change? When t becomes larger and larger.
Then that means that term becomes smaller and smaller.
Smaller. So in the limit, what do you get when t goes to infinity?
Means that goes to 0.
Okay, so it's Cm over C. We cancel C, we get M. So first observation, is from the solution, we know that the PT will increase to M as P go to infinity. That's our first observation. Okay, we'll have more about this next time. Any questions?
No.
No, Zichen? If no, I will